Welcome everybody. My name's Andy Rivenis. I'm a product manager, work for Oracle. Actually, we probably have as many Oracle people here as we do potential customers. But actually in the database development group, so I'm not part of sales or marketing. So our focus today is going to be more on technology. I thought that since this was more of a developer-focused conference, that I would forget about a lot of the use cases and the other stuff we talk about and kind of tell you how database and memory works and how it achieves the kind of performance that it does. Oh, and I will make these, we kind of worked out a deal. These slides will be available to you, so apparently they're going to allow you to download them. If you have questions later, we're actually trying to be very open. Part of the reason we come to these kind of conferences is to provide information. So my email address is there. If you have a question and you can't find an answer on our blog or you want to tweet me, feel free, because I'll be more than happy to answer your questions. One of our goals is to get folks to use database and memory adoption, because we think it's a really good product and we want you to think it is as well. So if you have questions, don't hesitate, just email me and I'll either try to answer them, I'll get somebody who can answer them, or maybe we'll point you to support, but one way or another we'll try to satisfy all of your requests. And again, that's kind of why we're doing this. Safe harbor statement. So database and memory. I have a slide on times 10. Oracle database has traditionally been a row-based database. Great for transaction processing. A little bit expensive trying to do analytics against it because we have to look at all of the data in the row store in order to traverse to get to the columns we're interested in, or you have to index it fairly heavily, which can affect your OLTP performance. Columnar-based databases have been around for a long time. Very, very good at analytics, scanning and filtering data very fast. Not so great at OLTP because it's very expensive to stitch those columns together into a row format in order to be able to do transaction processing. And with database and memory, you get the best of both worlds. So we haven't changed Oracle database. So starting in 12.102, database and memory was introduced as an option to Enterprise Edition. And of course, we've carried it forward into 12.2 and 18C, which is now available, 18.3 actually, on premises and 18C in the cloud. But the bottom line is that Oracle database itself hasn't changed. Database and memory is a pure in-memory columnar format. All of the data still exists in Oracle database in row format. All of the changes that you make actually occur to the row store. So database and memory isn't going to speed up OLTP, at least not directly. In other words, we're not speeding up inserts, updates, and deletes. What database and memory is focused on is analytic processing, analytic reporting. So that columnar-based format allows you to run your queries much, much faster than in the row store. And I'll have an example for you in a few slides to kind of point that out. We keep it simultaneously and transactionally consistent. So the data is always in the row store. We reflect it in the column store. We keep it simultaneously and transactionally consistent, very similar to what we do with an index, except we don't generate any undo and redo because the column store is pure in memory. So no on-disk formats have been changed. So all of your existing Oracle technology like RAC and DataGuard and RMAN backups don't change with database and memory. The secret sauce out of all of this is the optimizer. In other words, you don't say select from the row store or select from the column store. You say select from the object you're interested in querying, and the optimizer decides based on the entirety of your query at parse time, does it make sense to access that data in the row store or in the column store? And that's kind of the 50,000 foot level of what database and memory, what it's trying to solve, the problem it's trying to solve, the use case that it's going after. And then what I'm going to really focus on, though, is kind of how it's all put together and how it works. So I did throw in this slide so if you've come over to the booth, and if you haven't, please come over, and if you have any questions, feel free to talk to us about it. But we have database and memory and times 10, both in-memory products from Oracle. Times 10 is a very different animal. Times 10 is high-speed OLTP or transaction processing, very low latency, very, very fast, robust product. It's completely different than database and memory. Many times customers think that, oh, well, you just took times 10 and put it in the Oracle database, and nothing could be farther from the truth. So database and memory, again, is columnar-based data in the Oracle database. Times 10 is a separate database product focused on high-speed, low-latency, high-speed transaction processing. Sam gave a session earlier today. I assume his slides will be available. Or stop by the booth. Doug is there right now and will be there for both the rest of today and tomorrow if you want to learn more about times 10. But that's kind of all I'm going to say about it. So very easy to get started with database and memory. We allocate data out of the column store, or actually we allocate data out of the SGA. So there's one initialization parameter you have to set to enable database and memory. I will say, I said earlier, it's part of Enterprise Edition. It is an option. So on premises, it costs you extra because it's an option. In Oracle speak, options cost money. Features are part of whatever you're getting. And so on premises, it does cost additional. In the cloud, it's in several different shapes. So the extreme performance, any of the Exadata flavors of Oracle Cloud, database and memory is available as part of that. So on premises, if you're configuring it, in-memory_size, that comes out of the SGA. So we tend to tell people, don't steal memory. You need to think adding additional memory to support that memory for that columnar format or that column store. All you do is alter table in memory. We actually support tables, partitions, subpartitions, and materialized views. Can all be populated. They have to basically the data needs to be persistent in an Oracle database. And we can populate that in the column store in columnar format. Kind of the cool thing about database and memory is you don't have to put the entire database in memory. You can actually just put whatever objects you decide are current analytic objects that are going to get the benefit from being populated in columnar format, and the rest of it doesn't go into Oracle data or into data or the column store. Sorry, we don't populate indexes. It's just data, and I'll show you a little bit about why that is. And later, it is possible to drop analytic reporting indexes. Typically, folks, especially in mature applications, have had to very heavily index their row-based data in order to get analytic reports to perform reasonably well. Database and memory doesn't make use of those indexes, and in many cases, you can drop those indexes. You might say, well, big deal, I can drop my reporting indexes, so what? Well, indexes can very often take as much space as the actual table data takes, and it's actually relatively expensive from a transactional standpoint to maintain those indexes. So by dropping analytic reporting indexes, very often you can gain any headroom, any additional headroom you need to support the CPU processing for database and memory. And actually, typically, database and memory queries are so much more efficient, you can actually gain speed or gain CPU resources or capacity over not having database and memory and continuing the way your systems are currently architected. We do have something called the In-Memory Advisor. Of course, the Achilles heel of having to pick and choose which objects you want to put in memory, unless you decide just to put your entire schema in, which is perfectly fine. But many of our Oracle customers don't have terabytes of storage, memory storage in their individual servers, so very often it is a choice of what objects should I populate to take advantage of the memory that I do have. We have something called the In-Memory Advisor, which can be downloaded off of OTN. It's available in 11.203 and newer, supports 11.203 or newer databases. And you can run that against AWR and Ash data to give you a kind of a first cut or a first idea as to what makes sense to populate in the column store. In addition to that, people will naturally ask, yes, you have a question? So we have from 2:45 to 3:30. Let me, well, you'll wait? Okay. The compression advisor, typically folks will ask, well, now that I've got a tool to help me figure out what objects to populate, how much memory do I need? And you can use the compression advisor to tell you that. I circled, that's the default compression level in database and memory is mem compressed for query low. the compression advisor supports all of the compression levels that database and memory supports. So you can actually run it against your objects and get a pretty accurate picture of how much memory you need to have available in the column store to be able to populate those objects. And then it's fully integrated with things like Enterprise Manager, so you can graphically manage the column store in database and memory, as well as for SQL, for DBA types who want to do everything to SQL level. We obviously support that as well. All right, so that's kind of that's in a nutshell how you use it, and really that's all you have to do. We could actually just stop, and all you have to have is 12.102 or newer of Oracle database. You have to have some memory that you can allocate to the column store by setting the initialization parameter in-memory_size. You might run the in-memory advisor and compression advisor and decide what objects you want to populate, and that's it. That's all you do. You don't have to change any applications because it's a cost-based optimizer decision of whether you access the column store or the row store, and you're done. But of course, this is Oracle database, so there are cool things that go on under the covers, and that's kind of what I want to spend the rest of my time talking about. Oops, sorry. So again, it's a pure in-memory format. One of the big advantages of database and memory is that we only have to scan, because it's in columnar format, we only scan the columns that you have in your queries. We don't have to scan the entire row searching for each of those column values in each of the rows. Makes it very, very fast. In addition to that, we use compression. So columnar data, vectorized data tends to compress very well. We have multiple levels of compression. We usually tell people you can expect anywhere from a 2x to a 20x compression rate on the data you populate in the column store. So if you had, say, a terabyte of data that you wanted to populate, you wouldn't need a terabyte of memory allocated to the column store. You'd only need maybe 500 gigabytes or even less. And so obviously compression is one of those things where your mileage will vary, but we tend to get very good compression out of most of the data that we populate in the column store. And one of the cool things is it's available anywhere where Oracle database runs, database and memory will run. So you don't have to have Exadata. You don't have to be on the cloud. Certainly can be. There's some distinct advantages. But if you're running on commodity hardware, as long as you can run Oracle database 12.102 or higher, you can run database and memory. And it supports rack. So if you if you have a rack cluster on commodity hardware, it runs just fine. So that's kind of the nice thing about database and memory. It will leverage certain aspects of your hardware, like SIMD vector processing, but as long as Oracle database will run, your database and memory will run. And your applications will run, because as long as your applications will run against the version of Oracle database you have, they'll run with database and memory as well, because it's just part of Oracle database. It's not separate software you install. It's literally Oracle database fully integrated. Any questions? Any other? Well, I shouldn't even ask, right? We'll zip through, and depending on how we're doing on time, because I actually questions are usually the best, and with a small group like this, I'd be much happier making this more interactive. But I do want to cover a few things. So it's not a store. It is a store, not a cache. The buffer cache, typically you have a very small amount of memory. We cycle the physical blocks through the buffer cache as they're accessed. Very often, most Oracle customers have a much smaller memory footprint than they have total data, whereas database in memory is actually a store. I guess we'll have to go back to this one. So once you populate the object in the column store, and it's populated in its entirety, it stays there until you either say alter table no in memory, or the instance goes down. And so if you bring the instance down, the memory, and it's actually the same with the buffer cache. The problem with or the advantage of the buffer cache in that sense is that you're populating those blocks on a onesie twosie basis, whereas we're populating the entire object. I tend to tell people that in-memory is really an enabler. It's the columnar format that really gives you the speed up. But we populate the entire object in memory because we don't want to have to wait for disk I/O. To get this fast scanning, we need to have it in memory. So that's my picture for that. But so and it lives as part of the SGA. So in Oracle database DBA type people will understand that there's a system global area that's allocated at instance startup. And so the in-memory area, which is controlled again by that in-memory underscore size parameter, that's where it's allocated. So your only constraint is how large of an SGA you can allocate. Oracle database can basically address or essentially address memory much larger than you can get in any typical database server. We used to have the Sun big memory machines, which were like 32 terabytes, and we supported database and memory in those as well. Most of our Oracle customers are lucky if they run a terabyte per server, and obviously Oracle database can address way more memory than that. So there's never actually an issue with memory in the sense that we can use as much as you can allocate. So now we get a little bit of the nuts and bolts of things. I'm going to go a little bit fast just to get through everything. But I'm going to ask for, you know what? If you want to ask a question, feel free. We'll just do it. So in the column store, an object is going to be populated in the column store and is going to be made up of one or more IMCUs, in-memory compression units. If you don't have to remember all of this. I'm just it's good for an architectural standpoint. We have documentation in the in-memory guide, and then we have blog posts, actually an in-memory compression unit, IMCU blog post. So if any of this piques your interest and you want to dive deeper into this, we have lots of technical information that describes in much more detail how all this works. So please feel free to go peruse that. But the bottom line here is that in the in-memory area, an object will be made up of one or more IMCUs. And it'll have each IMCU will have a corresponding SMU, which is metadata associated with the IMCU. The IMCU is actually the columnar formatted data. And then each IMCU is made up of that columnar column-based data. It's pure columnar data. And we'll keep track of a row ID in addition because we need to be able to stitch that columnar data back together when we return it from SQL executions or to the upper layers of a SQL execution plan. It's literally, as we populate, we just read it right essentially off of disk and populate it in the column store. In 12.2, we introduced something called fast start to enable us to repopulate the column store a little bit faster. I'll have a slide about that. But the bottom line is you got to get it in memory somehow. I mean, it's got to go into memory, and that's part of the in-memory computing aspect of the product. In general, what we find is that IMCUs, it's not a hard and fast rule, but the default compression level will be roughly 500,000 rows. So depending on how large your table is, again, you get that one or more IMCUs. We won't populate objects that are 64K or less. So each of these IMCUs are made up of, do I have that in the next? No, I don't. I talk about, so each of these IMCUs are actually in the column store are made up of one or more 1 megabyte extents. And so since the minimum size of an IMCU can be 1 megabyte, we said anything smaller than 64K is going to waste that memory, and realistically you could get that faster from probably the row store anyway since it's so small. We just do a logical I/O against the block and we'll get you that row data or those columns out of that row data, and it didn't make sense to populate that data in the column store. So the next question folks will typically ask when they see all of this, they'll say, okay, so how do you keep it in sync? So what's the deal? Do I have to worry about performance? And I'm going to go through very quickly how we do that. There's actually a video that we did so the real world performance team in Oracle, part of Oracle database development are the hotshots. And we did a video that they had put together of real OLTP workload running database in memory. And what it shows is that as long as you have enough CPU headroom, you have enough capacity from your CPU, OLTP transaction rates are not affected by database in memory. In other words, database in memory, you can run your analytic reporting right on your OLTP workload. That's where the real-time analytics comes from. And it won't be affected because, remember, database in memory is literally just CPU and memory access. So as long as you have CPU overhead or CPU headroom capacity, you can actually run database and memory analytic reporting right against your OLTP workload and not affect that workload. And again, we have a nice video out there if you want to, bless you, if you want to see an example of it. So the data is in the column store and it's in the row store. You can't populate anything, hold that thought, but in general, all of the data that you populate from the column store will reside in the row store. So inserts, updates, and deletes, I said database and memory doesn't speed those up because those happen in the row store. It's the Oracle transaction processing. We generate undo and redo. It's all recoverable. You get reconsistent views of the data. Nothing changes because we haven't changed any on-disk formats. So if we change data in the row store, if you do an insert, an update, or a delete, we mark that data as changed in the column store in those SMUs. I talked about SMUs being metadata. We keep track of the data that gets changed, just like we do with an index. It's actually less work with database and memory because we don't have to generate any undo or redo. There's no on-disk formats because none of this persists. So we mark those a row as being changed in a journal. And the changing transaction can still see that changed data because it's reconsistent. No other transaction can see that data just like we do in the row store database. But that data, so if you're scanning, say you change some data with DML and then you start scanning, you'll see both copies in the column store for your transaction. Nobody else sees it because nobody sees the difference in the row store either. So Oracle's transaction processing mechanism hasn't changed. So we can scan the IMCU and then we scan the SMU journal. So anybody else, did we get to commit? We did not get to a commit. So you may have changed multiple rows. We keep track of this in the journal. Once that data gets committed, whoops. Sometimes I hit the. Once that data is committed, then we'll have, in this case, we'll have multiple, say we have multiple changes to a particular IMCU. Subsequent transactions then, when they're scanning the column store, will not only scan the column store, the IMCU, but they'll scan the journal as well. They'll see that this data has been changed. Keeps disappearing on me. Okay, let's go back. There we go. They'll see that that data has been changed, and we'll pick it up from the row store. So we'll pick up change data from the row store. Then subsequently, we'll repopulate the change data, either based on a threshold or a time, and then that data will be completely clean, if you will, again. It'll look like, maybe if I can go backwards, it'll look like that. So no changes will have occurred. And this is just an ongoing process. And so conceptually, it sounds like, oh, it's going to be slower to scan data that's been changed in the column store. And what that real-world performance demo shows is that in the real world, you never see the difference. It's so fast and so efficient. And typically, data that's been changed is resident in the buffer cache. And so you just don't see the difference. It takes a very, very high DML load to show any problems with keeping data consistent or even seeing any slowdown. The data is always consistent, but seeing any slowdown. So it's one of the questions that folks will very often ask, because conceptually it seems like, oh, it's going to be a big problem. The reality is it isn't. It's very efficient. As part of the repopulation process, we actually do, so we don't have to repopulate an entire object in the column store. We just repopulate IMCUs that have data that's changed. And we can do that with, we have some very efficient mechanisms that allow us to do that, again, to make that, and it all happens in the background, makes that very efficient, and again, so you don't see the differences in, so essentially it allows us to do mixed workload performance with providing very fast analytics on OLTP systems, so you don't have to always have a data warehouse, or you don't always have to have a data mart or a decision support system. You don't have to replicate data to do your reporting. You can literally do it right on the source data. And again, that's the real-time analytics portion of it. Sorry, that's a little fast, but I'm feeling pressured to get through this. So if you do have okay, so are there any questions? Let's just stop. Okay. Yes.
You also mentioned that the Columnar memory thing is an option and not a feature. Are the advisors option or a feature?
Okay, so 2 questions there. So I said the in-memory advisor is available. It's actually a separate piece of software and supports Oracle Database 11.203 or higher. And then the next question was, sorry.
I'm basically asking whether those advisors come for free.
So the Memory Advisor is no cost to you. You can download it off of OTN. The only cost was accessing AWR or ASH data requires the diagnostic and tuning packs. So because you're accessing AWR data, and that's no different with database in memory or without. And then I said database in memory for on-premises is part of Enterprise Edition, so it's an option, and it does cost extra to license database in memory. So those are the 2 questions?
No, basically, I just wanted to know whether they go hand in hand. It looks like I can download this.
Yes, you can download In-Memory Advisor, and you don't have to use database in memory. Yes.
So then, basically, kind of gives me like what if scenario. If I put on the columnar store at a later point in time, how much? What is the advantage I'm going to get out of it?
Say that one more.
By running those advisors,
Yes.
I'm hoping to get some incentive to put in this option at a later point in time.
Okay.
Right? I'm assuming that's what this code.
Yeah, actually, typically what people do is they know they have a problem, right? Their analytic reporting, either they can't tolerate the delay in extracting that data to, like, say, a data warehouse or decision support system, or they know their reports are running slower than their business requires. So they already know they have a problem, right? So typically people will run the in-memory advisor, especially when 12c was relatively new, but they haven't upgraded, they're still on 11g. So they want to know, does it make sense for us to upgrade to 12c and implement database in memory? So usually it's not like a year later we're going to upgrade the data or add database in memory. It's usually a fairly quick turnaround is kind of the idea, because your workload will change over time.
You said 2x to 20x compression.
For compression, yes. So the question is, I said you can expect a 2x to 20x compression rate on when you compress with database and memory. It is dependent on the cardinality of the data. What we do with query low is we use symbol replacements basically for the data. So the more common values or the less distinct the data, the better it's going to compress. We also do run length encoding, and we have in the higher level, the capacity versions uses zip-like compression. So even if you have fairly distinct values, you can still get some pretty decent compression rates.
I have another architectural question.
Okay, all right. So how do I get data in and out of the column store? Alter table sales in memory, alter table sales no in memory. At the partition level, you can choose individual partitions. So think maybe a time dimension, data warehouse, for instance, those current partitions you might populate in the column store, and older partitions you might take out of the column store. On Exadata, we support Flash, which I'll talk about. So you might think I'll have my most current partitions in memory. I might have my little bit cooler or older partitions in the Flash, and I can take advantage of Columnar in both those environments. Also, we have something called automatic data optimization and an 18C automatic in memory. Our goal is ultimately to make this idea of populating objects in the column store completely automatic. So we've created initially policies to allow that, and then an 18C automatic in memory, which uses heat map data exclusively if you allow it. And we're on a journey to full automatic in-memory population or management of the column store, because we can also evict older segments that are no longer being active. You're no longer selecting from them. I don't want tongue-tied there. And so based on heat map data. So the database already keeps track of a lot of that data, and we can leverage that to put the most active segments in the column store and then flush out or evict the least active segments to make that automatically managed. I said earlier, tables, partitions, subpartitions, and materialized views. We don't support IoTs or hash clusters. We're working on the IoTs, but they're really OLTP type structures, so that was not a priority, and hash clusters I don't think we'll ever do. Out-of-line lobs, we don't populate in the column store. Inline lobs, we do, and that comes into play, especially when we talk JSON data. But typically, lobs aren't very analytic in nature, which allows you, yep, good, I let that slide in, which allows you to exclude columns if you choose. So not only you can say alter the whole table and populate that in memory, but if you have columns that you're not accessing analytically and you're maybe short on space, or you have very large lobs that you don't, inline lobs that you don't want to populate, you can exclude columns. The only caveat to that is if you exclude columns and then you select from them, we have to go to the row store for everything. So it's an all or nothing in that case. I did a recent blog post on that too, if you want to look at the details. So then the question usually comes from people will ask is, well, why don't I just cache the entire table in the row store? What's the big deal? It's in memory. Why would it be a difference? And so here's an example that I use out of the hands-on labs that we do, and I do an in-memory by example, and it shows that when I do an aggregation on the total order price we use the star schema benchmark, so it's a line order table for our fact table, fully populated in the column store runs in 1/100 of a second, almost instantaneously. From the row store, what I do is I allocate a keep pool and I populate or cache the table entirely within the keep pool, so there's no physical I/O. It takes 8 seconds on the same exact system. So it's almost an order of magnitude difference in performance between the row store fully cached and the column store fully cached. So apples to apples comparison. So how do we do that? We only access in the column store, we only access the columns that we need to that are in the query. We have compression. 2x to 20x, we have 5 levels of compression, so we get very good compression. We have something called in-memory storage indexes. In other words, those IMCUs that I showed you, we actually keep track of the min-max values of each of the columns associated in those IMCUs. So if the data we're going to scan doesn't pass the min-max of the column we're looking for in that IMCU, we just skip it. So the fastest way to do something is to not do it at all, and that's kind of the idea behind in-memory storage indexes. And then we do SIMD vector processing. So I tell people you think of it as array processing. So the modern Intel and Spark CPUs have SIMD vector instructions. Solaris and Linux support those registers, I should say, support those instructions, and the Oracle database takes advantage of that. So then we go from scanning millions of rows per second per core in the row store to scanning billions of rows per second per core in the column store. And that's how you get from 1/100 of a second to 8 seconds. That's the difference. And so all of this together is the technology aspect of database and memory and why it's so much faster to scan that data in the column store versus scanning it in the row store. In addition to that, there's some secret sauce with the optimizer. Because let's face it, you don't have to change your applications to run with database and memory. There's got to be how do we do that? And it's because we're dependent on the cost-based optimizer. You don't say select from the row store, select from the column store. You just say select from your object. And the optimizer, based on cost, decides does it make sense to access that data through the column store, or does it make sense to access that data through the row store, possibly an index access. Again, that's why you can run OLTP, mixed workloads. You can run OLTP and analytic reporting in the same database for the same applications. So all of the existing optimizer rules for the row store still apply. So you have to get that stuff right. That's kind of what that slide tells you. And then at parse time, the optimizer goes and looks at the data in the column store, the data you're going to access. We pick up, how many IMCUs are there? How much of the data is in the column store? Because it could be that you populated an object and either it didn't fit in its entirety in the column store, which means some of that data we'll get from the column store, some of it we'll get from the row store, which is a good point to bring up, is even if all of the data isn't populated in the column store, or say you did a massive update or maybe an insert, direct path insert, your queries won't get errors. The data that isn't currently populated in the column store or maybe has changed will get from the row store. So your query will run regardless. You won't get an error because it couldn't find data in the column store. But the optimizer knows how much of that data is populated, and there is a tipping point where it'll say, you know what, not enough of that's populated or too much of it's changed, we're going to go to the row store to get that data. So your applications can run literally unchanged. Obviously, if all of your data isn't populated in the column store, or we decide to go to the row store, the performance is probably not going to be as good, but your application will still run and you can rectify the problem. But you can see this actually in an optimizer trace. It wouldn't be Oracle database if we didn't give you lots of choices and lots of information. So there are many ways to see all of this information. And again, we've talked about that in our blog posts, in our in-memory guide that we have in the documentation. So that information is available if you want to, literally go down to the decision making that occurs. And so we keep track. So the other thing, so basically what I did is I gave you a slide of the things that the optimizer, the cost aspects of that the optimizer takes into account when it does the parse. And this occurs at parse time. So once you've parsed the query, then we don't have to redo any of this. And so the big thing is both I/O costs and CPU costs, because the optimizer is CPU costing aware now in later releases. So the optimizer enhancements, so based on all that, the optimizer has some tricks up its sleeve as well. And the first one is when we choose to scan data in the column store, we can push function-based aggregations like mins, maxes, averages into the scan. And so what I tell people is the ultimate database and memory query is one where all of the time is spent scanning and filtering and essentially joining the data in the column store, and you get a result returned back from that and don't have to do anything else. That's the ultimate. Now, we don't always catch the ultimate, but all of these pieces get us hopefully to that goal of getting as close as possible to spending all of our time satisfying the query with the scan of the data in the column store. So with that said, data scans, pushing filter predicates and min-max function-based aggregations can all be pushed typically into the scan of the column store, or that object in the column store. And you'll see this in an execution plan. We actually tell you what we're doing. In addition to that, actually that's what that says. Got a little ahead of myself. In addition to that, we can turn joins, typically hash joins, not typically, but we can turn a hash join into a scan and filter operation. And it may be that rather than doing a nested loop join on an index, it'll make more sense to do a hash join accessing that data in the column store. The magic behind doing, and we typically can get a 10x performance improvement on hash joins. Hash joins with database and memory can leverage something called a Bloom filter. Bloom filters aren't new to Oracle database. They've been around since 10G. And what I have is a nice little diagram here that I don't think I have enough time to walk through. But the bottom line in a hash join, and I actually did an Ask Tom session with Maria on hash joins. So if you're interested in how database and memory leverages hash joins in detail, I would recommend going and looking at that Ask Tom session. But the gist of it is a hash join will typically join two row sources, a smaller row source and a larger row source. The smaller row source will scan, apply any filter predicates in memory, apply any filter predicates, and we'll create a hash table in the PGA. In addition to that, we'll create, very often if we have a filter predicate, a Bloom filter. And a Bloom filter is basically just testing set membership. So it's essentially a bit vector, a fairly dense memory structure. And we can actually use that Bloom filter. Rather than having to go in a normal hash join, we'd scan the larger table and we'd go take a look at the hash table in the PGA and see, do we have a match? Do we have a match? Do we have a match? And if we do, we'll pick up the payload columns. With the Bloom filter, we can actually apply that during the scan and effectively do the join during the scan and filter of in this case, the sales table. So we get a 10x performance improvement. You get all that for free. You don't have to do anything as long as you have in-memory enabled, the optimizer can take advantage of this access path and provide a significantly faster join performance than a traditional hash join. Does that make sense? Cool. And you actually will see that in an execution plan. You'll see, you'll see the join filter create as we're scanning. Well, that's really bouncing around. Or in this case, a date dimension table. And then you'll see join filter use as we apply that Bloom filter to the line order table. It's not just one Bloom filter, though. We can do multiple Bloom filters. So if you have a star query with, say, multiple dimensions, the star schema benchmark actually has 4 dimension tables and a fact table. You can actually see 4 Bloom filters applied to the scan of the line order table as part of that. So we can do more than just a single Bloom filter. And actually, I won't go into the details. I do in the Ask Tom hash join session. But Oracle Database is smart enough to be able to cheat and normally we can only join 2 row sources at a time. With multiple Bloom filters, we'll do a write deep tree, and we'll actually join all of the dimension tables at the same time effectively with multiple Bloom filters when we scan the fact table. If you understand what a swap join inputs and a write deep tree is, great. If not, I would encourage you to go take a look at our Ask Tom session if that interests you. Or you can Google for write deep trees as well. So in SQL processing, typically we're doing left deep trees, and so we're only joining 2 row sources. Oracle Database is smart enough to cheat and allow us to use multiple inputs or multiple dimension table joins during a scan and filter operation. And in-memory aggregation. This is actually very cool. There's actually an entire white paper dedicated to describing this. In an execution plan, you'll see something called vector group by. You'll only see this if you have database in-memory enabled. Effectively, what this allows us to do, really? Man, 10 minutes, guys. All right, so there is a whole white paper that talks about this. The cool part about this is not only can we do the join as part of the scan and filter operation, we use key vectors rather than Bloom filters because we use a dense grouping key, and what we essentially do is we create an in-memory report accumulator, and we actually perform the group by aggregation during the scan and filter operation as well. So now we got 10x performance improvement. We can get another 6 to 8x performance improvement doing in-memory aggregations. But what I usually tell people, the bottom line to remember with database in memory is, database in memory, if you're spending a significant amount of time scanning and filtering data, joining data, or aggregating data with a group by, then database in memory is going to help you. And these are the 3 aspects of database in memory, along with obviously the ability to do things like SIMD vector processing, scanning data, just columns we need, using in-memory storage indexes that make database in memory so fast. So again, scanning and filtering data, joining data, and aggregating data with a group by provide this speed up. So essentially what we're able to do is we're able to do the group by during the scan. So we've scanned our dimension tables, we've created a multi-dimensional in-memory accumulator, and then we're scanning the fact table, applying our key vectors rather than Bloom filters, and then aggregating that data as part of that scan.
I'll talk about this tomorrow if you want to skip this. So that
Okay.
we're running out of time.
All right. So that's Tertanker. He's at Tertanker. So actually, this is a big deal for us. Tertanker is actually the vice president in charge of development for all of ×10 and database in memory. Also NoSQL recently. But and he's going to talk tomorrow. I have a slide at the end that he's going to talk tomorrow. I have the time on it. So if this is of interest to you, I'd strongly recommend you come hear his talk tomorrow morning. Do you remember what time it's? 10 o'clock. 10 o'clock. I have it on one of my slides here. So this is just more information about how database or in-memory aggregation works. I do want to, though, touch on, and you'll see vector group by, which you won't see that access plan in anything but an in-memory enabled query. Now, the funny thing is this works on Exadata for storage scans as well. And even if you don't have all of your data in the column store, say you have a couple of your dimension tables are in the row store, and you'll see may see a table access full and not in memory, we'll still leverage vector group by. And we'll actually leverage Bloom filters as well. As long as database in memory is enabled, you get all of these optimizer enhancements available to you, whether or not you're fully in memory or not, which kind of goes along with the ability to run your queries even if not all your data is populated. So we've done a lot of improvements in database in memory since we released. 12.102 was July of 2014. So we've had 12.2, and now we have 18C. So we've had a lot of releases and a lot of changes. One of the big changes was the ability to support the database in-memory columnar format on Exadata Flash. So now you can go from maybe having a terabyte of memory in DRAM to having many terabytes on Exadata flash and be able to leverage that data or that flash storage for database and memory formatted data. But one of the cool things about this part, though, is it's all automatic. In other words, if you do a smart scan, we'll automatically reformat the data into the flash cache in columnar format. So that's one of the big reasons to consider Exadata or Exadata on the cloud. But I'm not in sales, I just want to point that out. We added, I'm going to skip over these features because I really want to talk about rack in the time we have left because of the scale out. Because I've heard when we were in the demo grounds, a lot of folks are talking about scale out and the ability to get very large memory footprints. And so I want to make sure I cover that. But join groups, what we've basically done in 12.2 and 18C, once the basic product is there, so we're not doing I/O any longer. We're basically just accessing data with CPU and memory. That's all you'll see like I said, in the ideal in-memory query. So we focused in 12.2 and 18C on two things: reducing that CPU footprint even further to make your queries even faster, and making it more automatically managed. I talked about a little bit about ADO and automatic in memory and our work that we're doing to make the contents of the column store automatically managed. So join groups is a way to improve that. In-memory expressions is another way. We have automatic capture. We support JSON not only in the database but also in the column store. And we have something which I think is the coolest feature, in-memory dynamic scans. So we can dynamically parallelize our scans of data in the column store without you having to do anything like fire up parallel query or have auto DOP enabled. We'll do this automatically based on Resource Manager. So you can truly make your access to the column store dynamic and as high as performing as your resources allow. In-memory external tables, support for external tables, in-memory optimization. All of this is documented in our white paper, 5 minutes. And so what I did want to cover is scale out. So Oracle Database supports not only single instance, but rack. And database and memory, because database and memory is part of Oracle Database, also supports single instance and rack. So if you can only get, say, a terabyte of memory in your store in a single server, and you can have you can have a cluster with 4 nodes and have 4 terabytes of column store. Since it's scale out, it's shared nothing. So we do have options in Exadata to duplicate data, but the actual scale out is basically treats it as not shared data. So we don't ship IMCUs or data across the interconnect. We actually use parallel query to run against a rack database. And so we leverage all 4 nodes, in this case a 4-node example, to run your queries, which gives you excellent performance and the ability to have very, very large column stores, very large memory footprints. And I wanted to point that out. In 12.102, we required auto DOP. In 12.2 and above, you just have to ensure that your DOP, your degree of parallelism, is at least as large as the number of nodes you have. But if you think about it, one of the really neat aspects of this, and I mentioned this in a blog post that I did on in-memory dynamic scans, is that with a DOP at least as great as the number of nodes, and then in-memory dynamic scans, you can dynamically parallelize your data access to your column stores across a rack cluster. And that's pretty cool, because if all you have is CPU and memory access, you're then essentially your performance is gated on the speed of your CPUs. And if you have a serial query, then you're gated on the speed of a single CPU. So the only way to speed that up is to parallelize that data. So Oracle Database has supported parallel query since like Oracle 7, but with in-memory dynamic scans targeted at database and memory, you can now have dynamically parallelized workload, and that's pretty slick, I think, anyways. You guys might not, but I think it's pretty neat. And on Exadata, you can mirror your IMCUs. So if you're on Exadata and one of the nodes, so you're on rack, typically people say, well, what happens when one of the nodes goes down? Do I lose all the data in the column store? And I don't lose the data because it's still available in the row store. And the answer would be yes. On Exadata, you can actually mirror that data so that you can preserve SLAs, because we'll have that data on at least one other node. And you can actually do it on all 4 nodes if you want. You can duplicate all. The reason you might do that would be to handle partial partition-wise joins. In other words, being able to having dimension tables duplicated on all of your nodes, joining against a partitioned fact table, and you can actually do the entire join on each of the individual nodes. So there's actually a performance benefit in addition to SLA, not really high availability per se, but an SLA preserving architecture if you have Exadata. Man, did I go through that fast. No 50 minutes, I put a lot of stuff in there, but it's all pretty key information. This is, again, Tirthanker's talk tomorrow at 10:05 to 10:30, it looks like. The room didn't show up. I picked, oh well, the main ballroom, okay. And that's tomorrow. Again, if you, and I'll make these slides available, we're going to create a PDF right after this. My email address. We have information available on OTN, on oracle.com. We have a blog that has not only lots of technical posts, but kind of an index, I call it the portal, into all things database and memory. So we have videos, we have customer testimonials of how they're using, how our customers are using database and memory. Lots of technical information, and anything that you get puzzled or stuck on, feel free to email me. Thank you very much. So we'll, I guess until we get kicked out, we'll all take questions.
So my question is, I think you probably answered a little bit in the context of a rack, where you have 4-node rack and you have shared netting architecture. The columnar data is now on 4 nodes.
Yes.
So I was kind of thinking a little ahead of the slide. So where I was going to ask you pretty much was that if you have an in-memory data grid, all of it is if. So if you have an in-memory data grid, and then say my query, because let's say I'm going to run analytical workloads, and if there's a possibility for us to have this columnar data available in the in-memory data grid, so that my columnar workload gets shifted to the compute node in the grid, so that the actual database itself is free of dealing with the, I mean, it has to preserve the columnar data, it needs to ship it out to the data grid, but beyond that, running queries on top of the, the columnar data and all that is now shifted to a compute cluster.
No, so you,
Like a rack, but let's say if I
well,
have a whole rack,
the closest I think you could come to that would be a sharded rack system, where you're sharding across, and database and memory supports Oracle sharding. So you could do that way. But you're still constrained within the Oracle database, because it's database and memory is part of Oracle database. You're constrained to that architecture. So we can't just pick up data out of Oracle database and put it somewhere, right? Exadata comes close to that in the sense of storage servers. We're running smart scans or or we can do flash access of database and memory columnar data. We support sharding in various forms as long as it's Oracle database. You could have rack clusters that are sharded across a shard. But as far as taking data out and just, yeah, that's not, that's.
is it even, what do you call that, in the roadmap of, let's say, timestamp?
You want to take that, Tirthanker? Here's Mr. Roadmap, so.
It's really, as Andy said, it's very difficult to decouple this piece. It's an Oracle native data format. And there's no good mechanism of doing it without having an Oracle instance running this code. So I understand the price issue there. The rack and sharding is the best way to scale this up. You can deploy a timestamp cache against Oracle in memory, and some people have done that. And the timestamp cache can be, you can build your own scale-up architecture with that. It's not column-based today.
Yeah, it's not.
There is something on the roadmap of timestamp to support Columnar eventually, but timestamp with in-memory row format and indexes actually works really well. A lot of people believe you need Columnar for analytics. The real thing is you can get similar performance with indexes. The reason indexes are generally not a good solution is because they're expensive to maintain. But if it's a read-mostly environment, you can certainly use timestamp with indexes. And we have many customers using timestamp as a cache for infrequently changing data, which they have indexes on in the timestamp here, and get very quick response times for. That's a solution we can certainly provide today. Taking the memory technology and separating that into a separate store, I just don't see that as being on any roadmap and anything soon. Besides, I won't even know how to do it. Forget about,
Now you can go the other way, though.
I'm sorry?
You can go the other way. You can bring external data into the column store without having to materialize it. Now I understand, but you can go you can do the opposite side of it. So you can actually bring externalized data into the column store without having to materialize it in the database. But ultimately, we're going to operate on data in a column store format, either in Flash or in DRAM. Sure.
The other thing is data is one thing, but all the optimizations and operations that is similar to all of that, either unless you're game to coding it yourself on an external store, I mean, go for it.
Okay, well, thank you for attending kind of a whirlwind presentation of the technology, so thank you very much.